In this video, we're going to look at a few exam problems on Maclaurin series. So, first one here, find the Maclaurin series for ln 1 plus e to the x up to and including the term in x squared. So, since they didn't invite us to use the results from the formula book, we won't. And it's also 5 marks, and it just wouldn't be if you're just plugging it in there. So, what do we have? We have f of x is what it is. Ln 1 plus e to the x. F dash of x is the derivative of 1 plus e to the x, which is e to the x, over 1 plus e to the x. Now I want terms up to x squared, so I want the second derivative as well. So quotient rule here. So v u dash, which is just e to the x, minus u v dash. U is that, and then derivative of 1 plus e to the x is e to the x, all over v squared. Now I could, I'm sure, simplify that numerator quite a bit, and in fact when I look at it, it really will simplify because I've got the e to the x times e to the x subtracting. But just to make the point, I'm going to show you that I'm not actually going to, because not the whole point, but like one of the benefits, one of the things you can do to speed up a Maclaurin series is not bother neatening things up. We don't care about a nice version of any of these. We just want to evaluate them at 0. So f of 0 is ln of 1 plus e to the 0, which is ln 2. At the first derivative at 0 is e to the 0, which is 1 over 1 plus 1. And then the second derivative at 0 is 1 plus 1 times 1, which is 2, minus 1 times 1, all over 1 plus 1 squared. So that is a quarter. I think that's all I need then. So it means that ln 1 plus e to the x is approximately equal to, or I could just do a dot dot dot, ln 2 plus a half x, and then plus, well, it's a quarter x squared over 2, so that'll be an eighth x squared, plus dot dot dot, and we're done. Okay, next, contrast that with this question. Using the standard results from the list of formulae, MF19, or otherwise, find the Maclaurin's series for e to the x plus a quarter e to the minus x, up to and including the x squared term. So it's only 2 marks, and it's only 2 marks because we're using the formula book. And so, using the result from the formula book, all we're going to get is that this is, well, up to the x squared term, we have all of e to the x, so that's 1 plus x squared over 2. And the same thing, but this time a quarter, and then we're subbing in minus x, so 1 plus minus x, so that's minus x, plus minus x squared over 2, so that's plus x squared over 2. Neaten it up, and you can see why this is only 2 marks now, because there's just not very much to do. Plus a quarter, minus a quarter x, plus 1/8 x squared. So in total we have 5 over 4, plus 3/4 x, and then we've got x squared over 2 plus an eighth of x squared, so that's plus 5/8 x squared, plus dot dot dot. So they make it obvious when you can use the formula book. Okay, and then a really tricky one here. The variables x and y are such that y equals 0 when x equals 0. Okay, and it is an implicitly defined curve, so relatively fiddly. Show that dy by dx equals minus 3/4 when x equals 0. So I'm going to have to just differentiate this implicitly, but that's not too bad. It's product rule for the first one, so u and v dash plus u dash v, so u dash is 1 and v is y. Next, it is chain rule. So power comes down, drops by 1, multiplied by the derivative of what's inside the bracket, which is 1 plus dy by dx. Equals 0. Now absolutely don't bother trying to rearrange to find an expression for dy by dx. Just sub in x equals 0, y equals 0. What do we get? We get a 0 plus 1 times dy by dx, so dy by dx, plus 0 plus 3 times 0 plus 0 plus 1 squared, so that's 1, brackets 1 plus dy by dx, 1 plus dy by dx equals 0. So in total we have dy by dx plus 3 plus 3 dy by dx equals 0, and yeah, 4 dy by dx equals minus 3, and dy by dx equals minus 3/4. So no particular drama there. We're heading towards now finding Maclaurin series for this function up to the x squared term. So we know that y is 0 and x is 0, so that's the first term, 0. We know what dy by dx is when x is 0, it's minus 3/4. We now need to find what the second derivative is when x and y are 0. And we know that at that point dy by dx is minus 3/4. So we're going to have to differentiate this. Not as bad as it looks. What do we get? Well, it's product rule here. So u v dash, and v dash is just the second derivative of y, plus u dash v. U dash is 1 and v is just dy by dx. Differentiate y, it's dy by dx. Now we've got a bit of a monster here. It's probably prudent to split this up into a u and a v, but I'm just going to go for it. Here's my u, here's my v. So it's u v dash. So u is 3x plus y plus 1 squared. V dash, I differentiate this bracket, and it's, well, 1 differentiates to 0, and it's d2y by dx squared, plus u dash v. So u dash is here. So power comes down, drops by 1, multiplied by the derivative of what's inside the bracket, which is 1 plus dy by dx. That's u dash, and then I've got v as well, which is 1 plus dy by dx. Okay, that's the sort of that's the sort of thing that you write down, that you hope someone who doesn't know much about maths looks over your shoulder and thinks you're a genius writing down such an incredibly long formula. Okay, time to sub in. X equals 0, y equals 0, dy by dx is minus 3/4. So 0 plus 1 is 1 times the second derivative. So d2y by dx squared plus 2 lots of dy by dx. dy by dx is minus 3 over 2, so that's actually minus 3 over 2 for both of these. Then it's 3 lots of 0 plus 0 plus 1 squared, so that's just 3 lots of the second derivative, plus 6 lots of 0 plus 0 plus 1, so that's 1, times 1 plus dy by dx. 1 plus dy by dx is 1/4, times 1 plus dy by dx, which is 1/4. And all of that equals 0. Okay, we're almost there, because we have 4 d2y by dx squared. Now let's evaluate everything else we have. So it's 6 times 1/4 times 1/4 plus negative 3 over 2 is minus 9 over 8. Get that over onto the other side, and that's 9 over 8. So what we have is d2y by dx squared equals 9 over 32. And now we can have our Maclaurin series, because it's y is equal to, well, it's the function y evaluated at 0, which is 0, plus the first derivative evaluated at 0, which is this, so that's minus 3/4 x. Then it's plus the second derivative times x squared over 2, so it's that over 2, so that's plus 9 over 64 x squared. So nice simple, plus dot dot dot. Nice simple-ish quadratic expression for this monster of a function. Just for fun, let's go over to GeoGebra and just see how that quadratic looks compared to that function. Okay, well, here's our function. In the end, it actually doesn't look too complicated, although it's got some sort of slightly strange wobble in it. Okay, well, here's our function. Well, not a function, implicitly defined curve, which, I mean, doesn't look too bad. I mean, it's got some odd wobbles in it. It's almost just a straight line. Let's see what our Maclaurin series looks like. Well, it was y equals, so we got minus 3/4 x, that looks not bad, plus 9 over 64 x squared. And it's kind of doing what we want, right? It doesn't look like the curve far away from 0, but zoom in, and yeah, it looks pretty good. So nice to see that it actually does work in reality. So definitely go ahead and try some exam problems for yourself, and I'll see you in the next video.